Today's packet that you picked up says transformations on it, and we will be covering transformations for the next 3 classes. Okay, so transformations will be classes 16 through 19. So this is going to take us through next Wednesday's class. Okay, so there's transformations, we're spending 3 full classes on it, and so it's a very important topic in terms of functions, because you're going to be using this idea not only throughout the course, but in the courses that you take after this. So now for transformations, we have only, even though we have 3 classes, we only have 2 homework assignments for transformations. And those homework assignments are homework 16 and homework 17. Those are the only 2 homework assignments. Homework 16 is due next Wednesday, which is March 12th. But as soon as class is done today, you can start working on it over the weekend. And in fact, if you read some of your book, you probably could even finish it. But you have until next Wednesday to do the homework that's assigned today. And the homework that will be assigned on Monday, homework 17, you have until next Friday to do. Okay. March 14th. Okay, so don't forget, you also have project number 2 is due next Wednesday. So if you have any doubt about the data that you've picked for your project, you should probably try to check it out with me at Monday's class so that I can make sure you're moving in the right direction, okay? Now, I also asked you to hand in your linear regression homework on Monday. I'm not going to collect that, okay? I'm not going to collect the linear regression homework from your packet. I think you all know that that's important to do for any assessment that you have and for actually learning how to do linear regression, but I won't require you to pass it in. So today's class, we're going to be working individually, and so I'm going to need folks to stay very focused today and to really kind of put your nose to the grindstone. And this is where I hope we get today, up to this point. I'm hoping we can get to this graph right here, which is about 4 or 5 pages in. We can stop at this graph. If you get here, we're going to stop today. Okay, and what I'm going to do is I want you to work with your, either individually or with your table mates. And as you do number 1, before you move from 1 to 2, have me come over and check what you've done and make sure you're working in the right direction and you understand what all your questions are. Once I check it off, you can then proceed to 2, and then I'll check 2, and you can proceed to 3. Okay, the one that I'm going to let you cross out that you don't have to do today is number 4, Roman numeral 4. This does not have to be done in class. Okay, do not do in class. You can do it over the weekend if you want, but I won't require you to do it in class today. So you could circle that or do whatever you want. Okay, so again, our hope is to get up to this graph if possible. So you have an hour and 5 minutes. Use your flags if you need them. There will be no lecture today. I'll just be working with all of you individually. Okay, this transformation video is being recorded to help anyone that missed the class or for online students. This packet is meant to be done individually by you, and you can use this video to check the work that you've done. So anything that I'm explaining here, you should have tried to on your own, and then you should be checking with the video. So the first problem that you have is to graph by hand the function f of x equals x squared. Now, many of you will recognize f of x equals x squared as a parabola, your basic, what we call our basic parabola. And in our transformation sections, we're going to refer to this basic graph as a parent function. That's often the terminology that we use. This is our parent function. Everything else that we do to x squared, all the kind of changes we make to it, you can sort of think of as offspring. So we've graphed x squared here. We put 0 in, and when we square 0, we get 0. When we square 1, we get 1. When we square 2, we get 4. And when we square 3, we get 9. And since x squared is an even function, we have points, the opposite values of x at exactly the same y values across the axis. So negative 1, 1, negative 2, 4, and negative 3, 9. Okay, so there's my basic function. And now I'm being asked to graph in a different color 3 new functions. Well, my graph doesn't have all of the possibilities that your sheets have. So I actually just did g of x in green, and I did k of x, h of x, excuse me, in purple. So to graph g of x, I noticed that g of x, let me keep that in the same color so we're not confused. G of x is x squared plus 3. And x squared is my original function, f of x. So I could, if I wanted to, rewrite g of x as f of x plus 3. So what this says is for any x, find the output by squaring it, because that's what f of x says to do, then add 3 to all the outputs. So when I square 0, I get 0. So if I add 3 to it, I go up to 0, 3. When I square 1, I get 1, and then I add 3 to it, so I have 1, 4. When I put 2 in for x, I square it, I get 4, and then I add 3 to it, I get 2, 7, and so forth. So g of x is x squared plus 3 is the graph of x squared plus 3 is this green graph that you see here. Now h of x says take f of x, which is x squared, and subtract 4 from all the outputs. That's what the graph of h of x looks like. So if you were actually creating a table, you would probably start with the same exact x values that you did originally. And to find h of x, you're going to square each one of your x values and then subtract 4 from it. So this would be 9 take away 4, which is 5. This would be 4 take away 4, which is 0, etc. So each of my points, let's see, negative 3 was 9. When I subtract 4 from 9, I get 5. So the point negative 3, 5 is on the graph of h of x. And that's what you see right here, negative 3, 5. Negative 2, originally when I squared it became 4, but when I take 5 away, 1, 2, 3, 4, excuse me, what am I taking away? I forgot. 4 away, right? I'm going to go from 4 down to 0. So I have this point right here, negative 2, comma, 0. My origin, 0, 0, now becomes 0, negative 4, and so on as I move along my x-axis. So this purple graph here, this parabola, is x squared minus 4. All right, so now we're asking you to describe what has happened to the original graph f of x to get these new graphs, g of x, h of x, and k of x. So we can say that g of x shifts the graph of f of x up 3 units. Some of you might prefer different language. You might want to say g of x adds 3 to all of my y values of f of x. Some of you might say I raise the graph of f up 3 units. Okay, so there's lots of different ways to say it, you notice that all of the points on f of x have been increased by 3. On h of x, which is this purple graph, all your points have been decreased or moved down by 4 units. So h of x shifts the graph of f of x down 4 units. We're literally just moving the graph, our original graph, up and down the y-axis, whatever number appears after x squared. And k of x, even though I didn't graph it, would shift the graph of f of x down 8 units. Okay, so now we're asking you to find the output for the same value of x. So we're saying, okay, let's assume x is 0. What's the output, the y value, when we put 0 into our f function? What's the output when we put 0 into our g function? Similarly with h and k. And we're asking to verify that these values go down or up depending on what we set up here in C. So f of 0 is 0. The origin here, the vertex, the origin is the vertex. F of 0 is 0. And g of 0 is 3 units higher. It's 0, 3. So that verifies that my graph of f of x has been moved up 3 units. H of 0 is 0, negative 4, and that's moving this point down 4 units. So that verifies this observation. And k of 0 is negative 8, which is moving this point down 8 if we had it graphed here. And similarly, if you find these points, I'll leave those there for a few minutes for you to take a look at. They also correspond to what we discovered up in C. Okay, so we're now going to try something very similar, but now we're going to use a different graph. Let's go back for a minute and observe something that we didn't ask you, which has to do with the domains of our functions. So if I asked you what the domain of the function f was and what the range of the function f was, you would have told me that the domain is from negative infinity to infinity, and that the range, I hope you would tell me, is from 0 to positive infinity. So one of the things you want to take a look at is how does the transformation of the function change the domain or the range? Sometimes it changes one and not the other. You have to look at what's being done to the actual function. So if we now take a look at the domain of G and the domain of F, in the range of G, we want to see how has the function's domain of range been affected by this transformation right here, by adding 3 to all the output. So we take a look at the graph, and we see that the domain hasn't changed at all. All x's are still allowed into the function, but the range now, the smallest value of my range is 3, and it continues to go up to positive infinity. So my domain is unchanged. It's still negative infinity to infinity, but my range has become 3 to infinity. So you should try that on your own. You should try the domain for h, the range of h, and similarly, domain and range for k. See if you observe a similar result. Okay, so the next function we're going to graph, again, a basic function here is the square root function. So f of x equals the square root of x is our basic function, or as I mentioned to you earlier, it's called our parent function. So the first thing you should have observed is what the domain of this function is. What's the domain of f? Well, we know that we can't take that the square root of a negative number is not a real number, so we can't graph it with the Cartesian coordinate system because the y-axis and the x-axis represents the real numbers. So we know that to graph this, the first value that we could graph is 0. The square root of 0 is 0. And then we go out to infinity. There's no end to the x values we can put in the non-negative direction. So this axis here, all the x values along this axis are allowed into my function f. The range of f, the smallest value will be the square root of 0, and then that will also continue to increase without bound. There's no limit on my output. So now, as I would do with any function I'm not familiar with, is I might try some various numbers, put them into my function. The square root of 0 is 0, and I would plot that, 0, 0. And then square root of 1 is 1. Square root of 2 is the square root of 2, and the best thing I can do is represent it with a decimal approximation, like 1.4, maybe right there. Square root of 3 is about 1.7, and the square root of 4 is going to be out here at 2. So I'll draw my square root graph. Oops, missed it a little bit, like that. Okay. So now I want to see what transformations I'm being asked to do. So very similar to the first series of functions, I'm adding something to the original function f of x. I'm adding 2 to the output values. So we sometimes say we're acting outside the function because we perform whatever the function tells us to do on x. That's the square root in this case. And then we're adding something to it. So that essentially adds 2 to all of the y values, or the output values, or outputs. So if I just go here to my original function and I add 2 to my output, then 0, 0 now becomes 0, 2. So let's make that red. 0, 2. 1, 1 now becomes 1, 3. 2 square root of 2 now becomes 2 square root of 2 plus 2. So I just move up 2 units. 3 now becomes 3 square root of 3 plus 2. And then out here I've got, instead of 4, 2, I have 4, 6. Excuse me. Instead of 4, 2, I have 4, 4. So I'm going to say that's right there. So again, it's this kind of slow curve increasing. Okay, so you try the next two at your seats, or hopefully you've already tried these. I'm going to turn the recording off for a minute in case you haven't done them. Okay, so now I've put in the other transform functions. H of x is square root of x minus 5. That's represented right here by this blue curve. This is h of x equals the square root of x minus 5. And k of x is the square root of x plus 5 is the purple function. So this is k of x. K of x equals the square root of x plus 5. So similarly, if we were to describe what happened to our functions, we would say g of x is let me see, I think I'm going to start this a little different. Let's say g of x moves the graph of f of x up 2 units. Just like we found in the first example with the x squared situation. Now h of x, our picture of h of x, this blue graph here, has all the outputs move down 5 units. So we could say moves the graph of f of x down 5 units. And similarly, k of x moves the graph of f of x, similar to the number 1, up because of the plus 5, but it's going to be up 5 units. So I'm going to fill in the values for f of 0, g of 0, h of 0, and k of 0, and hopefully they'll match what you have found. So f of 0 is 0, g of 0 is 2, h of 0 is -5, and k of 0 is 5. F of 9 is 3, g of 9 is 5, h of 9 is -2, and k of 9 is 8. Why didn't I ask you to find f of -4? Because x equals -4 is not in the domain of f, and the square root of -4 is not a real number. Why didn't I ask you to find f of 5? Well, I could have, but f of 5 is the square root of 5 is an irrational number. So some of you might have said, oh, it's a messy number, or we can't approximate it with a decimal, or ugly, unfriendly. You all have a different way of saying that. Okay, so there we have the parent function x squared with some vertical transformations, and the parent function square root of x with some vertical transformations. So where we've shifted our graphs up and down the y-axis. So now let's take a look at x squared again, and you should be able to quickly graph x squared. Since we just spent some time doing that with number 1. Okay, so here we have x squared. So we're going to label all of our graphs. That's like a little title. And now what are we going to observe? Well, it asks you to observe on your calculator g of x equals x plus 3 squared. So some of you might have a sense before you graph this what you think is going to happen to our red graph f of x. And you have some ideas when you look at each of these, and then you go to your graphing calculator. So let's take a look. I'm going to do this all on the graphing calculator. I'm going to put all of my graphs in. So I'm going to put in y equals x squared. Well, let me clear everything out of here. You might run into this since we just did some linear regression that you still have your stat plots turned on. So the first thing you have to do is turn off your stat plots, or else you're going to get some kind of error when you go to graph. And now we can see all of our stat plots are turned off. So now let's go in and put in our parent function x squared again. And now we want to, before we even get to square our input, we're going to change our input here. So this is a little different than the graphs we just looked at, the function. So this is x plus 3 squared, okay? Now I want to be able to differentiate that graph from y1. So I'm going to change, instead of having it be dots, I'm going to change it. So let's see, what do I want it, whoops, what do I want to change it to? Let's see. Whoops, hang on. So I'm going to keep entering. Oh, that's a nice thick. So I'm going to have y2 be x plus 3 squared, and it's going to have this nice thick line to mark it. Let's see. Let's what our next function is. X minus 4 quantity, the quantity x minus 4 squared. So let's take a look at that. X minus 4 squared. And let's move over here and let's see what we want to make that look like. Okay, we'll use those little black triangles. Okay, so we'll want to have a window. We should probably use our standard window, zoom 6. And there's x squared. There's x plus 3 quantity square. And there's, x minus the quantity x minus 4 squared. So you may have some surprises here. It may not look like what you thought it was going to look like. So let's, I want to get my, oops, let's get this back. I want to get my camera up here. I always do this. I always do it in the wrong order. So let me fix this. Cut. I have to have my camera available before I do my picture. So let's say I want to get a nice picture of these graphs off of my graphing calculator here. So let's capture that. There we go. And we can put it on here. Okay, so let's see. Blow this up. Okay. So here's our original function, our parent function x squared. Goes like this. So this is f of x equals x squared. This nice big dark black function over here is the function g of x equals the quantity x plus 3 squared. And over here to my right, I have h of x, which is x minus the quantity x minus 4 squared. Okay. So usually what I find is that before students actually look at these graphs, when they see x plus 3 quantity squared, they think that the vertex of this parabola is going to be to the right because they see the plus 3. So they're often surprised that it's actually moved to the left. And similarly, when they see x minus 4 squared, it's moved to the right and not to the left. And often I ask students to take a look at where the output value is. In other words, our first point on this parabola right here, our vertex, is 0, 0. And notice, in order to be located at 0, since our x values are all going to be increased by 3, they're going to have 3 added to them, we have to make them 3 units smaller in order to get to this same point 0. In other words, in order to get to be a 0 here, I have to put in a number 3 units smaller than 3. And that would give me 0 squared. So everything, this point is moved to the left 3 units. Let's take a look at our point 3, 9. 3, 9, or let's say 2, well, we'll go with 3, 9. Let's say 3, 9 is right here. So now I'm saying, okay, to get to being 9, I have to have a 3 in here. So x plus 3 has to equal 3. What's inside here has to equal 3. So to solve that equation, x must now be a 0. So 0 plus 3 square is 9, because 3 square is 9. So notice this point originally was 3, 9, and now it's 0, 9. So every single point on this red parabola has been shifted to the left, moved horizontally to the left 3 units. Okay. And similarly over here, to get back to being 0, I want x minus 4 squared to equal 0. So that means x minus 4 has to equal 0, because 0 squared is 0. So x has got to be 4. And we see right here that if I put a 4 in and then subtract 4 from it, I get right back to 0. So here, before you even get a chance to perform your function, which is squaring your input, we're messing around with our input. Here, our input has to be 4 units bigger than it was originally to get us right back to the same y value. And with our blue function, 3 is being added to x, so all of our x values have to be 3 units smaller. Okay, so it's a little different than what you might expect intuitively. We're now moving horizontally, right and left. We're not moving vertically up and down. So, and then the other big difference besides this directional change is that when we see an addition of 3, it doesn't go to the right, it goes to the left. When we're moving vertically, plus 3 moves in the direction we think. It goes up, it increases by 3. And the x minus 4 is a shift to the right. So we can say g of x shifts. I'm just changing the language. I could use moves. Okay, I could use moves instead. I'm just going to say shifts the graph of f of x to the left. 3 units. H of x shifts the graph of f of x to the right 3 units, 4 units. And then k of x, I didn't graph that, but it follows the same idea of what happened in number 1. It's going to shift the graph of f of x to the left 2 units. And then we can find f of 0, g of -3, h of 4, and k of 2. So notice now, when we were doing our vertical shifts, we kept our x values all the same and found out what happened to the outputs. Now we're hoping to keep all of our outputs the same. To get 0, our inputs had to change. X now has to be 3 units smaller. X here for H has to be 4 units bigger because 4 is being subtracted from it. And in K has to be 2 units smaller to bring us all back to 0. You can verify these last 4 here. Hopefully you'll find a similar result. Whatever f of -2 is, f of -2 is 4. So hopefully when you've done g of -5, h of 2, and k of -4, you've also gotten the same output value. Okay, so that's working with the parent function x squared. Now, I didn't ask you to do this in class today, but you should, just for some practice with your square root function, take a look at this and see if something similar happens. So again, you're inside your function because your function is to take the square root, and you have a -3 here. So the g of x is going to shift the function f of x to the right 3 units. So instead of starting at 0, 0, we're going to start out here at 3, 0. And you can see h of 3 is the square root of 3 minus 3, which is 0, and that's 0. So it's going to shift the function 3 units to the right. Similarly, this will shift the function f of x 2 units to the left. This one will become 4 units to the left. Okay, so let's take a look at this statement here. If f of x is our basic graph, which means our parent function, and g of x is our original function plus d, so the constant is being added outside of the function f of x, it moves f of x in what direction? If you're adding a constant, whether that constant's positive or negative, this is affecting all of your output values, so it moves your function vertically. If d is a positive number, then the graph moves up. If d is a negative number, then the graph moves down. And this is a vertical shift. Okay. H of x is the transformation on f where we've added c to the input value x. So we're already affecting the input before we perform the function. Now we don't know what the function is here. The function could be squaring this or square rooting it or absolute value. We're just saying we're changing our input. Anytime we change our input, it moves our function horizontally. And if c is positive, it moves the graph left. And if c is negative, it moves the graph right. And this is a horizontal shift. Okay. So this is how you want to start a summary page, because we're going to be looking at lots of different transformations over the next couple of days. So you may want to start a page where you have a summary of your different transformations. So This would come under the vertical shift, and this would come under, the next one would come under horizontal shifts. Some people like separating them, but this is kind of a nice way to write it. It's a nice summary. Okay, so now I'm asking you to take a look at this particular function here. What is the basic graph? Again, we're asking what is the parent function here? Well, you see a square root. So our parent function, let's call it something different than f of x, we'll call it g of x, is the square root of x. So we notice that two things are going on here. We're affecting both the input and the output because we're subtracting 4 from x before we take the square root, and then even after doing that, we're adding something to the output value. So what is the vertical shift? The vertical shift is up 5 units. That's this part right there. And the horizontal shift is happening inside. And it says subtract 4, so that means I'm moving right 4 units. So how do you graph this? Well, you could always start with some basic values of your original function. Let's start with those 4. And if I'm going to shift up 5 units, that means up 5 units, all my y values are going to have 5 added to them. So I'm going to do that first. Okay, so I've changed all of my y values. So that's 5's been added to them. And it says I'm going to move to the right 4. So that means all of my x values are going to also increase here by 4 units. So I'm going to have 4 here. Now my 5 stays the same. I'm going to have 5 here. I'm going to have 6 here. I can't fit the square root of 2 plus 5 in there. And I'm going to have 8, 7 here. Okay, so those are now my new points if I perform both of these transformations. So instead of graphing 0, 0, 1, 1, 2 square root of 2, and 4, 2, which I could graph that really quickly just so we can compare it. 1, 1, that's the scale is 2 here, so we're going to go in between. And then 2 square roots of 2, and then 4, 2. So here's our function, parent function, f of x equals square root of x. And now my transform function, which moves right 4 units and up 5 units, are these 4 points. So instead of 0, 0, I'm now 4, 5. So I go 4, 5. Let's use a different color. Here's 4 and here's 5. And my next one is 5, 6. So 5, 6. My next one is going to be 6 square root of 2, 5. So 6 square root of 2, 5. That's about right there. And then let's see, the last one is 8, 7. So 8 would be way out here and 7 would be about right here. So here's my g of x. So that's my transformation. Oops, I got my letters backwards. This is g of x, sorry, and this is f of x. So the question of the hour is, I chose to move up 5 first, change all my y values. So I was literally like picking up this function right here. Like if I took this function and I copied it and I just literally moved it up 5 units. Okay, I did that first. And then I moved it to the right 4 units. That should be about the same. That's how I got the new transform function. So my question is, would it matter if I move to the right 4 units first and then up 5? So that's a question I want you to think about. Okay, so You can try this one at your seats. There's two things happening here, and we can check it when you come to class. And we will start the next class with this function here. This is a piecewise function. So this is where I want you to stop for today. This is a piecewise function, and we're going to do some transformations on this piecewise function. Okay, so we'll stop this first video for class 16 here, and we'll pick up with this problem on during the next class.